In this final section of chapter 4, we want to take a closer look at Taylor's theorem and look at some computations and examples of things you can do with Taylor's theorem. We will see kind of how we can really use them to approximate some concrete functions, complicated functions, by polynomials, and we will take a look at local extrema again and see that Taylor's formula, or Taylor's theorem, then gives us the answer of how to distinguish maxima, minima, or non-extrema. So far we only have a necessary condition, Fermat's theorem of local extrema, for local extrema of differentiable functions, and now we will establish a sufficient criterion with which we can really determine from a point which has vanishing derivative if it's a minimum, a local minimum, local maximum, or none of the two. We will see this later on. But first we'll see some concrete examples of Taylor's theorem. Before I start, let me give you a reference to another YouTube video, namely to a channel that I really recommend in general. It's called 3 Blue 1 Brown. I think many of you will probably have heard of it. It's a mathematician, I think he was formerly at Stanford University, who is really an expert in visualization, and so he really tries to explain stuff in the right way and has some amazing animations of some mathematical situations that I could never do on the blackboard in the same way. And he has a very nice video on the Taylor series. I think it should be just called Taylor series, the video. So just you have to search 3 Blue 1 Brown Taylor series on YouTube and you'll find it. I'll put the link to this video in the comment section to my video here. So you can also look it up there. And there he basically, there's a beautiful animation of the Taylor polynomials of the sine function. And you can really then see why this is good at approximating and what Taylor polynomials really do and so on. So I really recommend you strongly to take a look at this video maybe before you continue watching my video here. Okay, so we take a look at another example. So the sine function is nicely covered in this video. We take a look at another complicated function, f going from -1 to plus infinity to r. F of x is given by log of 1 plus x. This shift by 1 is really so that the formulas become cleaner and nicer. We will see this in a bit. But we want to study Taylor polynomials of the logarithm function, just shifted by 1 in the argument. So what do we know about this function? We've seen that the logarithm is differentiable, and we know that x plus 1 is obviously differentiable. So as a composition of differentiable function, it's differentiable, and we can compute its derivative by the chain rule. We know that f prime of x, so first we need the derivative of the exterior function, so of the outside function basically, which is log, which is 1 over the argument, the derivative, so it's 1 over 1 plus x. By the chain rule, this is the same as, so here we do this by the chain rule. Oops. So now we have to multiply this with the derivative of the function inside the argument of log, but we see that the derivative of this is simply 1. So there's nothing more, and this is already the derivative of this function f. Okay, we see that this is a quotient of polynomials. And as we've argued before, this is then differentiable as often as we want, because kind of the differential by the quotient rule always becomes again the quotient of polynomials, very roughly. So hence it is smooth. And if f prime is smooth, obviously the one stage above, f itself is also smooth, because it's like only one derivative more, and now they all exist. So this implies that f is smooth. Okay, so much about that. Now we want to take a look at the derivatives. So we have seen, so f prime of x is 1 over 1 plus x, and now we want the second derivative, f double prime of x. So we could apply the quotient rule, which is a bit too much of work for this, because this is derived much easier by the chain rule. 1 over x, or 1 over y, to take a different name here, would be, the derivative would be minus 1 over, and then y, which is in this case just this denominator here, squared. So it's minus 1 over 1 plus x squared times the derivative of this function inside, which is again 1. So this is already the answer. In the same way, the third derivative of f. Okay, now minus 1 over y squared, for example, so if we have a different variable, this is the exterior function here in the chain rule. This we know how to derive this. This is minus minus 2 times 1 over 1 plus x to the 3, so this left as it was the argument, times the derivative of the argument, which is 1 again, so this is 2 over 1 plus x to the power of 3. And now you might already see the system behind this, so there's a general formula, and this is something you have to then to prove by induction, which I won't do here, but I strongly recommend that you kind of pause this video and do this slight computation for the induction steps. So the base case is this, but we need the induction step. So the kth derivative of f in x. So we see kind of, because we have to derive, and there's some, a negative integer will always be in here. So you can see kind of there's, with each iteration of the derivative, there's another minus sign. So it alternates between minus and plus and minus and plus and minus and plus with k becoming bigger. So this is then minus 1 to the k minus 1 times, and now we always kind of, when we derive this, we multiply with the exponent here. So there's always, this minus sign and some number getting bigger and bigger, and it turns out that in the end we have k minus 1 factorial divided by 1 plus x to the power of k. So this is true for all k in n and all x in minus 1 to infinity. Sorry for squeezing. So this is the general formula for the derivative here. Okay, what we now want to do is to determine the Taylor polynomials of this function in the point 0. So for the Taylor, we always, this point that I called a previously in Taylor's theorem will be 0. So log of 1 plus x at the point, log of 1. So we want to basically approach the logarithm near 1 by polynomials, only that we have this shift here because this is more convenient. Namely, we can now really easily compute the derivatives at 0, namely f to the k of 0. So what's this? Just take a look. This is minus 1 to the k minus 1 times k minus 1 factorial. And if we take a look at the denominator, this is just 1 plus 0. So this is just 1 to the power of k, doesn't matter. So this fraction is simply k minus 1 factorial. And this holds for all k in n. Okay, this means now we have the derivatives, and so we can write down the Taylor polynomials in 0. So this means that the nth Taylor polynomial of f of x with respect to the point 0. Sorry, I just said something wrong. Here's the general form of the Taylor polynomial of f in the point 0. So here would be x minus a to the power of k, but a is 0, so this doesn't matter. So we got this expression here. So we've got the derivatives. The only thing that we have to pay attention to is the case k equal to 0, in which case we just have f of 0 divided by 0 factorial, which is f of 0. So this is the same as f of 0 plus, and for the rest we can enter the formula we just established. So it's this here. So this is minus 1 to the k minus 1 factorial divided by k factorial times x to the power of k. F of 0 is by definition of f the logarithm of 1. And we know that the logarithm of 1 is 0, so this summand here is vanishing. Now take a look at this. We've got k minus 1 factorial divided by k factorial. And if you take a look at the definition, this just means basically that we can reduce the fraction by eliminating this. And here this is the same as k times k minus 1 factorial. So basically we can erase the factorial symbolically. So everything that remains is Tnf in x at 0 is the sum from k equal to 1 to n minus 1 to the k divided by k times x, which is a surprisingly simple expression. This is not that complicated as a polynomial. I mean, if we can just write this down explicitly, the first summand would be, minus 1 to the k minus 1. Okay. The first expression would be for k equal to 1, we have 1 here, 1 there, and here, x to the k, sorry, and 1 here, 1 there, x to the 1, so this is just x. The next one would get a minus sign, and this would be x squared divided by 2. Then we get a plus sign again and get x3 divided by 3 minus x4 divided by 4. and so on. So a nice little expression. And who would have thought this is connected to the logarithm? This is not really non-obvious. So by Taylor's theorem, we know now explicitly, we now know that the log of 1 plus x is this expression, the sum from 1 to n over minus 1 to the k minus 1 over k, x to the k, plus something remaining, plus r, I call the function Rn of x, for all x in minus 1 to plus infinity, where we know about the function r. So r is a function also from minus 1 to plus infinity to r. And we only know so far that it satisfies limit of x going to 0 of Rn of x divided by x to the power of n is 0. But we still don't know how big this gap becomes between log x and this polynomial. So the problem is what does this function do? So we can't say yet, but we will see later on that we will find some x for which this indeed goes to 0 if n goes to infinity. So where we can kind of approximate logarithm of 1 plus x by polynomials in a nice way. Okay, so much for the first example. I now do another one, another complicated function. So this was the first example. So this was the first one. Let's do the second part of the example. And now I consider another complicated function, the arctangent. This is a function from r going to minus pi over 2, if you recall. So this is a subset of r, of course. And we want to study this function and also want to take the point a equal to 0 again. And determine the Taylor polynomials of the arctangent in 0. So again, the arctangent is, tangent is the quotient of sine and cosine, and the arctangent is the inverse function of this quotient. So this is not something like you can put in a computer and it can give you the answer straight away. So this is something which involves a lot of computations to explicitly determine. So it would be good to have some function, like a polynomial, which is nicer and easier to compute and which approximates this good enough. Okay, so we've seen before that the arctangent is differentiable, and we've already computed its derivative. I haven't written down which example it was, but I have computed this explicitly. Arctan prime of x, we've seen that this is 1 divided by 1 plus x squared. Again, this is a quotient of polynomials, and we follow in the same way as we did in the first example. We derived that the arctangent is smooth. So this as in 1 arctan is smooth. Now, here it turns out if you want to iterate this computation and now compute the kth derivative, it's quite hard to find the explicit formula actually. You're welcome to try, but this you can derive by the chain rule and derive again and again. But the formulas there, you don't really see a system. It's kind of quite hard to determine. And there's a little trick with which we can do this, find an iterative formula or general formula for the kth derivative and derive this from this expression by simply reformulating this expression. So we want a formula for the kth derivative, arctan to the power of k of x. This is what we want to compute. Now, so the problem is here that in contrast to the situation in example 1, here we have, if we derive this by the chain rule, we have the exterior derivative, but this time we have a non-trivial derivative of this interior function, 1 plus x squared. This has derivative 2x, so there will be an additional factor coming in, and this kind of messes up the computation. Now, we do the following trick. So far, we've seen the derivative, and I've mostly considered real functions, but we can kind of artificially write the arctan prime as a complex function. Namely, 1 plus x squared, the denominator here. This we can write as the product of two linear polynomials in the complex numbers. Namely, this is the same as 1 plus ix times 1 minus ix. If you compute this expression, this is precisely x squared plus 1. This is just some fancy way of writing this. Okay, how does this help? I mean, the derivation rules is all fine for complex functions as well, so functions with values in the complex numbers. And the trick is the following. We can now decompose this into partial fractions, namely, this is the same as 1/2 times, and now let's write here 2 in a complicated way. We write this is the same as 1 minus ix plus 1 plus ix, and leave the denominator as it is. So you can see now we can decompose this into this part and that part, and now we can reduce these two fractions, because this then becomes the same as 1/2. And now here, the first one, there we can just reduce the second factor here, so it remains that 1 over 1 plus ix, and in the second one we can do the same thing. This is 1 over 1 minus ix. So we've reformulated this arctangent prime as a complex function, and now this is easier to derive, because now the derivative of this denominator here would just be I. So some constant thing which kind of gets multiplied, but no new variable, which kind of makes our function complicated, because constants, it's fine in deriving. Now, if you have this, namely in this way, let's do the first ones by hand. So what's the derivative of this? So arctan double prime of x. So constants don't matter for derivations. So this is now the sum of these two by our derivation rules. We can derive them individually. So now we can use the chain rule. 1 over y for y some variable would be, the derivative would be minus 1 over y, so y squared. So this is 1 plus ix squared. And now we just have to multiply this with the derivative of the denominator, which I said is just I. And so we remove this and write this already in the fraction. This is I. Okay, so this is, some explicit expression here. Here it's almost the same thing. So here we first get the exterior derivative here. This would be, the plus becomes a minus, so it's minus 1 over 1 minus ix squared. And now we have to multiply this with the derivative of the denominator, which is minus I. And so the minus and the minus together become a plus, and we get this expression. Okay, now we can do the same thing again. So in the same way, you can treat you can compute the third derivative of arctan. This is 1/2, and now we do the same. I just write down the results. So this is basically again applying this rule. This is minus 2i times minus I divided by 1 plus ix to the power of 3. Again, just chain rule computation. And here we get 2i times I divided by 1 minus ix to the power of 3. And now this is, from this observation, you can already guess the expression for the general formula, which is already something we can write down and which we need to prove by induction. But let me erase this to do this on a new blackboard. Okay, so the general form for the kth derivative is again proven by induction, which I will again skip here because this is a very simple computation, and I again recommend you to do this for yourself. Namely, the kth derivative of arctan of x is given by k minus 1 factorial over 2. This is kind of from the exponents that come in when we derive these functions contained in the big sum, in the parentheses. And inside we get that this is minus I to the power of k minus 1 divided by 1 plus ix to the power of k plus I to the k minus 1 divided by 1 minus ix to the power of k. So this again holds for all k and n, and for all x in R. Okay. So we've got this general formula, which I won't prove, but now we can compute the derivative in 0 straightforwardly from this formula. So the kth derivative of the arctan in 0, so we simply have to insert x equal to 0. So we see that in both cases here the denominator just becomes 1. So we get k minus 1 factorial over 2 times, and now everything that remains is minus I to the power of k minus 1 plus I to the power of k minus 1. And to simplify this, we pull an I to the k minus 1 out of this out of the parentheses. So we get k minus 1 factorial I to the power of k minus 1 divided by 2. And here we get minus 1 to the k minus 1 left, and this is simply 1. Okay, from this expression you can already see something quite simple, namely if this is minus 1, then this here of course vanishes, so the derivative vanishes. And this is minus 1 if this exponent is odd, so and the exponent here is odd if this k is even. So we get that all even derivatives vanish in 0. Arctan 2n in 0 is 0 for all n in n, which means that quite some summands in our Taylor polynomial have to vanish as well. Okay, now for the odd derivatives, we compute arctan 2n plus 1 in 0. So let's take a look. We get 2n plus 1 minus 1 factorial, so this is 2n factorial. Here we get I to the 2n divided by 2, and here we get minus 1 to 2n plus 1. And now it becomes quite simple because here we can see this is, of course, because this exponent is always even, this is plus 1. So this together is 2. Here we have another 2, so this and this cancel each other out. And by the standard roots for powers, I to the 2n is I squared to the power of n, which is simply minus 1 to the n. And now our I has vanished and we're back in the real world, so to say. So everything that remains is minus 1 to the power of n times 2n factorial. Okay, so yeah, for all, and this is true for all n in n0 this time, because the first derivative also fits in there. Okay, so now we got that. So now we can really write down the Taylor polynomials because we've computed everything. So the nth Taylor polynomial of, sorry, not f, of arctan in x at 0 is simply the sum of all, I don't write the full polynomial in there again, but we can see that also since the arctan of 0 itself, the value is 0, so the 0 summand vanishes as well, and there we see that all summands with an even index vanish because of this fact, so the only thing that remains is the odd ones here. So let's do this slightly differently. So t2n plus 1, so the 2n plus first polynomial, this just contains now the summand from 0 to n, and there we get only the odd ones because the other ones are 0, and so there we get for each k this expression, so minus 1 to the k 2k factorial divided by, and now since this is the 2k plus first derivative, here we get the 2k plus 1 factorial, x to the 2k plus 1. And this is already the expression. This, just to see that this, this is not, sorry, I forgot to reduce it. Again, these two here are very similar. This is just 2k plus 1 times this factorial. So this can be reduced with, with a factorial here. So the answer here is simply the sum from 0 to n minus 1 to the k divided by 2k plus 1, x to the 2k plus 1. So again, it's a simple polynomial which looks similar to the one of the logarithm, but if you see there's slight differences, let me just write down the first summands explicitly. Here we only have the odd exponents, so the first one would just be, for k equal to 0, we just get x, so this guy just becomes 1. The next thing gets a minus, and there we get x to the power of 3 over 3. The next summand gets a plus, and we get x to the 5 over 5, and so on, until we arrive at minus 1 to the n, x to the 2n plus 1 divided by 2n plus 1. So this is a clean formula for the the Taylor polynomials, and so we get that by Taylor's theorem. Let me just write down the statement once explicitly. Arctan x is the same as the sum from 0 to n minus 1 to the k over 2k plus 1 times x to the 2k plus 1 plus some function r 2n plus 1 of x for all x in R, where we know about the remainder function that the limit of x going to 0 of r 2n plus 1 of x divided by x to the 2n plus 1 is 0. Okay, this is Taylor's theorem, but still we have the same problem as before. We don't know how big the difference is between this polynomial and this arctan for some concrete x, and we don't know what happens if n becomes bigger and bigger. So if we really approach this, so if this expression really goes to 0, if n becomes very big. So we still don't know if it's a good approximation of arctan. And this is something we will see later on, but we need a bigger theorem for this. Before we do so, let me give you one example of things you can do with Taylor's theorem. Because you might think, okay, we have some function here, we don't know anything about this except for this one limit thing, so what can we do with Taylor's theorem? It turns out it can sometimes be useful to compute certain limits. And I will give you an example of this as well. Namely, so the aim is we want to compute two limits, which without Taylor would be, I don't know, almost impossible to compute, I guess. We want the limit of x going to 0 of arctan x minus x divided by x to the k for k equal to 2 or to 3. The simplest cases here. So this is divided by x squared or x to the power of 3. So this is something that, I don't know, without Taylor I would have no idea how to compute this. This is, we see that this goes to 0 and this goes to 0. So here in this case, okay, we might use the roots of L'Hopital. I haven't thought about that one actually. But still we would get a problem, since the derivative of the denominator would again always go to 0. So this might be a bit messy. So here's something where L'Hopital is not the best choice. But we can really simplify this, namely if we replace this by its representation by Taylor's theorem by a polynomial plus a remainder function. Namely, we have seen in the example, oh, sorry, forgot to mention. If you're now wondering, this was example 439, this is 441. There's a remark 440 in between, which I just wanted to mention orally. Sorry about that. You can see if you have the remark is if you have a power series. So if a function which is really given with a power series, you can see that the Taylor polynomials at 0 of such a power series, first you have to check that it's differentiable, and then you can see that the polynomials are really the first parts of the sum of the series. So we really just take a part of this as a this is really then the Taylor polynomial basically of the series are then given by the partial sums of the series. This is something I can't prove yet because we're missing some topics we haven't discussed in this lecture, but this will be done next semester. But I just wanted to mention, so for power series, there's also a nice methodical way. It's easy to see then the Taylor polynomials you get for free, basically. But sorry about that. So by example 439, we've seen that arctan. And now we do, it's one of the simplest representations by polynomials, namely we take the case of n equal to 1 in this formula. Then we simply get, this just says that we get x minus x3 divided by 3, which would be the Taylor polynomial in degree 3, so if 2n plus 1 is 3, plus some function r3 of x, where this function satisfies limit x going to 0, r3 of x divided by x to the power of 3 is 0. Okay, how does this help us? Let's insert this in the computation and start with the case k equal to 3. The limit of x going to 0 of arctan x minus x divided by x to the power of 3. So by this formula, this is the same as the limit of x going to 0 of x minus x to the 3 divided by 3 minus x plus the remainder. I just reordered the terms here. And this divided by x to the power of 3. And now we see that the x and the minus x precisely cancel each other out. So we get that this is the same as the limit x going to 0. And now we have minus x to the 3 divided by x to the 3. This is just minus 1/3. And the remainder is plus 3 over x divided by x over 3. But we've just seen that we know this limit. This thing here is just 0, and this is constant, so this is simply, so this is going to 0, so this is minus 1/3. So we've computed the limit, which is highly non-obvious because you can't really see from this formula that the result is minus 1/3 if you don't know the Taylor polynomial here. Okay, for k equal to 2, you can do a similar thing. Limit as x going to 0, arctan x minus x divided by x to the 2. This is now by the same idea as here. So the numerator is the same as before. So here this is the limit of x going to 0. And now we have in the numerator, if we already did this computation, minus x to the 3 over 3 plus r3 of x divided by x to the power of 2. So now it's come to think about this. What happens here is this is the same as the limit x going to 0 of, and now we divide here, minus 1/3 x plus r3 of x over x squared. And we don't know what this is a priori, but we can just artificially factor out a copy of x. Namely, this is then the same as the limit. If we pull just x out of the sum, x going to 0, x times minus 1/3 plus r3 of x over x to the 3. And now we know again this goes to 0. So what we get is that this expression here goes to 0, obviously. So here, theoretically, we have to form these brackets. So this goes to 0, obviously. This goes to minus 1/3, and this goes to 0. So the whole thing here, this goes to minus 1/3. And so since both of these expressions converge, we get that the limit is the product of the two limits, which is obviously 0 because this goes to 0. And so we've computed that limit as well. So this is a nice way of using these polynomial expressions to simplify your limits drastically. Okay, so now for the question. Let me erase at this point because now something new is coming. The next theorem is another version of Taylor's theorem, which is a bit more useful for concrete computations. Theorem 442. This is actually again Taylor's theorem, but this version is often called the Lagrange remainder form. For all French-speaking students, this is called the Lagrange remainder form. Sorry about messing up with the languages. Okay, Lagrange remainder form, namely, assume we have I an interval, and we have a function which is sufficiently differentiable. So assume we have fix some point in the interval a and I, then we take n in n0, and f from the interval to c is n plus 1 times differentiable. Okay, now we want to make a statement about the difference of f and its Taylor polynomial, and it turns out that for each x in I, and it's now, I will continue the sentence momentarily, we get that f of x, so is tnf x in A. Now, in the Peano form, we just know that there's some function which has a nice limit property. And here we can now really do an explicit computation, an explicit expression for this function. But this expression depends on the choice of x. So you have to be a bit careful. Namely, for each x in I, there exists some xi in I, which lies between a and x. And such that the following holds. F of x is its nth Taylor polynomial plus the n plus first derivative at xi divided by n plus 1 factorial times x minus I to the n plus 1. So this almost looks like another summand from the n plus first Taylor polynomial, except for this xi. And of course, keep in mind, this is not some fixed function here because this psi depends on x. Otherwise, we would get that every function would be a polynomial, which is obviously not the case. So here, this is really, you have to be careful as long as x is moving. But for some fixed x, you can really just have an expression for this form. And now if you have some estimates on the derivatives, as we shall see later, and if we can now find some nice estimate on this expression, this really helps in doing some computation. We will give the examples after the theorem, but first we have to prove this. So, first of all, if x is the same as a, this is obvious because then the Taylor polynomial, every Taylor polynomial, just by definition, there's this x minus I to the power of n to the power of k in these different summands. So there only f of a is remaining as a summand, and so everything just vanishes here. Of course, this is then 0 as well. So in this case, it is obvious. So we assume that x is not equal to a, and furthermore, we make another assumption. We assume, without loss of generality, that x is bigger than a. So other case is then basically proven in precisely the same way, so analogously. Okay, so we make this assumption. So now we do the following. We take m in R. We choose it in the following way. We choose it such that f of x is Tn f of x a plus, and now we don't know what the expression is, but we can always find some real number, which we at first we don't know anything about, such that m plus x a to the n, x minus a to the n plus 1, such that this is satisfied. So there's just some real number, and we now have to show that there's exactly some psi, such that this is then really the derivative divided by 2n plus 1 factorial, so that m is of this form here. This is what we need to show. Okay, so we recall x and I are now considered as fixed. What we now do is to consider another function in terms of x and a. Yes, we first put Pn of t to be, just to save some notation, to be the nth Taylor polynomial of f in the variable t at a. And we then consider the following function. G is going from I to, no, it's fine. G going from I to C, and G is supposed to be, G of t is defined as f of t minus Pn of t, so f minus the polynomial, minus m times t minus a to the m plus 1. And of course, we don't know anything about this m except that it has this property for t equal to x, which is a fixed number here. So this is just some function that so far we don't know much about. But we know that f is differentiable, the polynomial here is obviously differentiable, and this is differentiable. And it's n plus 1 times differentiable, since f has this property. And we can compute easily the derivatives there. And so far we first need the n plus first derivative. And the n plus first derivative of g, now by the standard derivation rules, is the n plus first derivative of f at t minus the n plus first derivative of the polynomial Pn, but Pn only has degree n. And we know that the n plus first derivative and all higher of a polynomial of degree n is just 0. So this is the derivative of this one is 0, and now we have to take the n plus first derivative of this expression here. And by the standard derivation rule, we see that this is m as a constant factor times, and now we get the exponent. So every time we derive, we put the exponent in front and lower it here by 1, and then put another exponent in front, and so on and so on and so on. So what remains there is m times, and after n plus 1 times, we get n plus 1 factorial times t minus a to the power of 0, just by the standard rule, and this is of course just 1. So we can erase this again and get this clean expression here for the derivative. Okay, moreover, if we consider the other derivatives, so the derivatives gk in the point A. So this time not for every t, but in the fixed point A. There we know that this is fk of A minus the kth derivative of the polynomial in A, of Pn in A. And this expression here, if we have some, so k should be lower than n plus 1, then we see that this is always some polynomial, power here with a positive exponent and with a 0 inside here. So this will be 0. So this time the other summand doesn't matter. But we've chosen, remember how we constructed the Taylor polynomials? They were just chosen precisely like that to have the property that this is equal to this. That the kth derivatives in this point A is the same as the kth derivative of the function. So this becomes 0 for all k between 0 and n. Okay, now we pull out the joker, namely, by our choice of n, m, so by definition of m, basically. We know that g of x is 0. This is precisely how we've chosen m. This is, g of x is precisely the difference of the two sides of this equation, so g of x is 0. And here we've seen that g of a is 0. So also g of a is 0. And now we have a differentiable function which is 0 at 2 points. So if I now would have an audience, I would ask, do you recall a theorem that is made precisely for this situation? And the answer would be yes, namely Rolle's theorem. By Rolle's theorem, this says that between two zeros of a function, there's a 0 of the derivative, which means there is some, it's called a psi1 between a and x. We've assumed that x is bigger than a, with g prime of psi1 is 0. But now we're in the same situation as before, namely now we know that g prime of psi1 is 0, and here we've seen that g prime of a is 0. And since this is twice differentiable, we can apply Rolle's theorem again. By another iteration of Rolle's theorem, there exists some number psi2 between a and psi1 with g prime of psi2 is 0. And now we can use Rolle again. Because now we know that g double prime at a is 0, g double prime at psi2 is 0, and so we have, and so on and so on. So we can just use this again and again and again. And so again, Rolle. And in the end, we get that. So this is just n times, so this is finitely many times, so I don't do induction or something. By Rolle's theorem in the end, we get some, there exists some psi between between a and psi n, which would then be constructed after n iterations in the same way with the n plus first derivative is equal to 0. Gn plus 1 of psi is 0. But then by construction, we have this formula here. So in this case, we get that 0 is f to the n plus 1 of psi minus m times n plus 1 factorial. And now we just have to bring this to the other side, divide everything by m plus 1 factorial, and get that m is indeed f to the n plus 1 of psi divided by n plus 1 factorial. And this is precisely what we wanted to show. Okay, this is the Lagrange remainder form. I really like this proof because it's such a beautiful little argument. Anyway, so this has a nice consequence before we come to the examples. So now we have an explicit form for the difference between the function and this Taylor polynomial. So this might be useful, might be not, but it turns out to be quite useful in some situations. Namely, we get also an immediate corollary, which is, again, a statement which is, if you read this, it's quite plausible and you think it's quite obvious, but so far we haven't shown it, and it requires some effort to prove it. Namely, if I is some interval, f from I to c is n plus 1 times differentiable for some n, n in n0. Now, if the n plus first derivative of some point x is everywhere 0, so if its n plus first derivative is entirely vanishing, then f is a polynomial of degree n. Of degree at most n, sorry. Could be smaller. And the proof of this is now fits within one line. I'll make a test if it really fits within one line. We can just apply Taylor with Lagrange form. So this is by Theorem 442. So now we get that, so for each x we find some psi with this expression, but we know that for every possible choice of psi, this is 0. So this is vanishing. So we get that by Theorem 442, f of x is equal to the Taylor polynomial, Tn f of x at a, for all a in I, x in I. So we can just choose some a and then find that f is equal to the Taylor polynomial, which is a polynomial of degree at most n. And now we're done. So this is now a nice little observation, which is really, you might think it's obvious, but it's not. So yeah, let me now erase, and then we'll consider again some examples.